Alright, so let's get into some spherical geometry, section 12.7. Our objectives are to compare Euclidean and spherical geometry, find distances on a sphere, find areas of spherical triangles as well. And our essential question is, how can you represent a line on a sphere? Alright, so let's just compare Euclidean to spherical geometry. So when we talk about Euclidean geometry at the beginning of the year, we talked about a plane being a flat surface that extends without end in all directions. And I have a visual here to kind of help us with understanding this sentence. You don't have to write or draw your images, but mainly identify the statement in your notes. And then compared to spherical, a plane in the surface of the sphere is different. It's not flat. It doesn't necessarily extend and go forever in all directions. So the surface of this sphere compared to the surface in Euclidean is flat versus not flat. Another major difference between Euclidean and non-Euclidean, or in this case the spherical, is that a line in a plane is the set of points that extends without end in two directions. So for example, we have line PR. And then over here for spherical, a line is the great circle. And our great circle is the line that's going through the center of the sphere. Great circle was also defined in our previous lesson when we did spheres. Alright, let's compare angles between the two geometries. For Euclidean geometry, an angle is between two rays. So if I have a ray here with a ray there, then I've got an angle in between. Again, on a flat surface. An angle between two lines is the angle between the planes containing the two corresponding great circles. So you can see that an angle within spherical geometry is going to look different than an angle in Euclidean geometry. So here's an example of Euclidean triangle. Here's the spherical geometry. So the fact that you have two right angles is not possible in Euclidean, but it is possible in spherical. Alright, let's focus in on some core concepts between these two geometries. For Euclidean geometry, let's take a look at plane P. It contains line L and point A that are not on line L. Well, in spherical, we have the sphere S that contains the great circle M. Remember, your great circle is a line inside of the spherical geometry. And point A that's not on line M. The great circle is M, so the great circle M is a line. And you can tell that the lines are clearly different between the two geometries. Next, the vertices of triangle ABC are points in plane P, and the sides are your segments. So the sum of the interior angles of a triangle is 180 degrees. So that means measure of angle A plus measure of angle B plus measure of angle C is equal to 180 degrees. That's in Euclidean geometry. In spherical geometry, let's take a look at our triangles in spherical geometry. The vertices of triangle ABC are points on sphere S, and the sides are arcs of great circles. The sum of the interior angles of a spherical triangle is greater than 180 degrees. So if I take the measure of angle A plus the measure of angle B plus the measure of angle C, that sum will be greater than 180 degrees. Now, some properties and postulates in Euclidean geometry are true in spherical geometry. Others are not, or are true only under certain circumstances. For example, in Euclidean geometry, the two-point postulate states that through any 2 points there exists exactly one line. Our implied statement, shortened down to 2 points, implies one line. So here's an example of 2 points A and B, and through those exact 2 points there exists exactly one line. So in Euclidean space are lines passing through 2 points, but in spherical geometry it's true in spherical geometry only for 2 points that are not the endpoints of a diameter of the sphere. The endpoints of a diameter of a sphere are called antipodal points. So here we have an example where 2 points on the sphere do not have exactly one line. They have more than one line. All right, our definition of antipodal points, it's 2 points directly opposite each other on a sphere. Points on opposite ends of a sphere's diameter. For a sphere, antipodal means the same thing as diametrically opposed. So here you have the great circle. Its endpoints are A and B. So we say that points A and B are antipodal. All right, let's take a look at example 1, where we're going to compare Euclidean to spherical geometry. We're going to tell whether the following postulate in Euclidean geometry is also true in spherical geometry. Drawing a diagram to support your answer will be helpful. It says that if there's a line and a point not on a line, then there is exactly one line through the point to the given line. In other words, our implied statement that we learned back in section 3.1 was that a line and a non-collinear point implies parallel lines. So here's a great illustration to support understanding whether this postulate would be true in spherical geometry. Now, parallel lines we know cannot intersect. That's true in Euclidean geometry. But the sphere shows that line L, in other words, a great circle, and a point A not on line L, we can see that there are several lines drawn through A, and each great circle containing A intersect line L. So you can have multiple lines passing through that same point A. So there can be no line parallel to L. So in conclusion, the parallel postulate is not true in spherical geometry. All right, let's talk about how to find distances on a sphere. Well, for Euclidean geometry, we learned that there is exactly one distance that can be measured between any 2 points. We use the ruler postulate to determine distances on a Euclidean line. In other words, the distance between any 2 points, so in this case A and B, implies the absolute value of the difference in their locations on a number line. And here's an illustration to help us refresh on the ruler postulate. So whatever point B is on the number line, subtract it from wherever point A is located, and whatever that distance is, it's always positive distance, which is the reason you have the absolute value. But for spherical geometry, there are 2 distances that can be measured between any 2 points. So let's check this out. We have this point, and between there I can get a distance. The distances are the lengths of the major and minor arcs of the great circle. So I can get this distance, which would be a minor arc, and then if I were to go the opposite direction, so along the dotted line and then come back around, that would be a major arc. And that would still be the distance between these 2 points, it's just in a different direction. Alright, so let's find the distance on the following sphere. So the diameter of the sphere is 15 inches, and the measure of arc AB is 60 degrees. Find the distance between points A and B. So remember from Unit 10, to find the measure of, to find the arc length, you have to set up a proportion. So arc length of any major or minor arc divided by circumference of the circle, which is 2 pi r, equals the ratio between the arc's measure and 360 degrees, because that's the total measure all the way around the circle, the great circle. Alright, so we substitute our values. We want to know the arc length of A to B. We know that the circumference is 2 pi r, or in other words, we can use pi times diameter since we know its diameter is 15. So 2r is equivalent to the diameter, so we can plug in 15 for 2 and r, getting us 15 pi. And then the measure of arc AB, which was told to us in our problem is 60 degrees and then totals 360 degrees. We'll say that this is y for arc length of ACB divided by 15 pi. And this time we need to take 60 from 360 because we're getting the other part of the arc. Multiply both sides by 15 pi and reduce your fraction to 5/6. And then that results in exactly 12.5 pi inches for the arc length, or 39.270 inches. So the distances are 2.5 pi, which is about 7.854 inches, and 12.5 pi, which is about 39.270 inches. Now let's talk about triangles in a spherical geometry. It's a little different. The area of a triangle on a sphere is pi r squared divided by 180 degrees times the sum of all the angles minus 180 degrees. R again is the radius of the sphere. Alright, so let's practice this formula for area of a triangle. Start by writing your formula. So pi r squared divided by 180. In this case we have angles D, E, and F all getting added together. Subtract 180. Now we substitute 10 because we know that the radius is given as 10. So 10 squared is 100. 100 pi divided by 180. Substitute the 95 for D, the 115 degrees for E, and the 105 degrees for F. Alright, and the sum of all of our angles minus 180 degrees is 135 degrees. 10 squared is 100. So you have 100 pi divided by 180 times 135. That all simplifies down to 75 pi inches squared. Type that in the calculator, you get approximately 235.619 inches squared. Alright, let's take a look at example B's area of triangle JKL. So first set up your formula. So A equals pi r squared divided by 180 degrees times the sum of measure of angle JK and L minus 180 degrees. Substitute all the values that you know. We know that the radius is 12, so 12 squared. And then 102 substituted for measure of angle J, 90 degrees substitute for a measure of angle K, and 78 degrees substitute for the measure of angle L, all minus 180. Alright, the sum of the angles minus 180 degrees comes out to be 90 degrees. And 12 squared comes out to be 144. So 144 pi divided by 180 degrees times 90 degrees. And that will all simplify down to 72 pi. And then the approximate value would be 226.195 meters squared. Alright, so the area of triangle DEF is 75 pi, or about 235.619 square inches. And the area of triangle JKL is 72 pi, or about 226.195 square meters. Alright, I leave you with M.C. Escher's Spherical Geometry artwork here. And see you in class. Bring clarifying questions. Get ready for non-Euclidean geometry.